This article is from 2012, but it does a great job capturing some of the things you only learn in practice about machine learning. That was the point of the article. And so I just wanted to share kind of my process. This was my second read through of how I highlighted it, what I learned, and this mind map I ultimately built from it. Okay, so this was a paper I read on vacation. I guess a little weird like that, where I feel like I always need to be doing something. And so having a paper to read on the plane was great. I also took some notes in my second brain, and that's what you see me referencing throughout the video. These are things that stood out to me or things I reflected on. Some of these are my own words. Some of these are from Googling or using tools like Perplexity or ChatGPT to go deeper on certain concepts I didn't understand. And so after going through the entire paper again, I pulled out some kind of key points again. And now these were things that stood out to me, things that I found relevant. I am Chris. I'm a staff data engineer on an AI research team where I build and optimize data sets for deep learning. I also like to understand the modeling side a bit more, so that's where a lot of these AI learning videos come from. And then I tried to map it all together here. And so let me just try to articulate what I was going for with this mind map. But this paper is really about machine learning. The goal of machine learning is to generalize well. You're trying to build a model that will predict some sort of output on unseen data. And the way you generalize well is you need to, as the human designing the learner, or as the human designing the experiment, you need to balance this trade-off between the model complexity, where you're underfit or overfit, and I'll get into that a little bit more, with the dimensionality and the size of the data set you have. So like how many input features you have, how big of a data set you have, and like what's actually possible given the constraints of human time and compute. Now, this process over here is something I kind of just pulled out doing a deeper dive. The intro of this paper kind of took a few things for granted. Right away off the bat, they're using a classifier as an example, and that got me thinking like, what other types of problems are we using machine learning for? Like, why just a classifier here? What is meant by this hypothesis space? And so you'll see sometimes throughout the paper, I put these red dots here. Those were things that I wanted to dig into a bit more. And so some of that made it into the final mind map, some of it did not. But anyway, so this process here is kind of like the overall ML workflow, or if you have to solve a problem, first understand the problem. Well, what are you trying to do? Then like, what's your data? What are your inputs? What are the output labels that you're trying to predict? Then pattern match that to some kind of ML problem. And that's like where this classification comes in. And other ML types of problems would be things like regression, clustering. I was trying to understand where ChatGPT or large language models fit in. And it's kind of, so it falls under the umbrella of like generative AI, obviously, but the actual like problem class is some kind of like sequence predicting, or it could even be a form of classification, I think was one answer I saw, because you're basically just predicting the next token from a library of giant tokens. I'm sorry if I'm butchering that. I didn't dive in too deep there, but effectively the problem type is pattern matching to what type of problem in ML are you able to represent the problem that you're trying to solve in the real world as. And then you build the learner. And this I thought was really interesting, this learner piece over here. So learner is just a representation. Basically, what type of model? Is this a neural network, a decision tree? Like, how are you representing the data to the computer that's going to crunch all your numbers? And then how are you evaluating it? How good is this model? What is your cost score? Or what is your optimization function? How do we know, or maybe optimization function, not to go there. How do we know if this model is doing a good job? And then the optimization process. How are you going to find which model in the hypothesis space of all possible models that exist, given the representation you picked? How do you find it? So for neural networks, this typically, like the type of model would be a neural network. The evaluation is often something like mean squared error, cross entropy. And then optimization is gradient descent. I don't know if I think there's variations on gradient descent, but gradient descent is basically like we're just searching the hypothesis space of things that are possible by finding the right parameters to make the best model that minimizes our loss function. So you design this learner, and this learner produces a model. And now what this article was really discussing was how do you get a model that's good, a model that generalizes to unseen data. And so the article offers quite a few kind of techniques or themes on this, but this is what I pulled out. Like in general, try to prefer simple, but simple models don't necessarily imply accuracy. Just simple is sort of a virtue for its own sake. There are various techniques you can use, like cross-validation, regularization. Building an ensemble of models seems to be better. The paper cites a few examples of where that worked really well in practice, where you combine multiple models. And in general, sometimes it's easier just to get more data, more good data. But the paper says one of the hardest things is to spend a lot of time on feature engineering, and you're often constrained by human time in making a good model, where you're just constantly iterating on things. And as a data engineer, I'm thinking, yes, data engineering is the backbone here and is often a bottleneck. I've seen that in my practice, where getting the data clean and ready for training is just such a huge time sink and a very important part of the work. So that was kind of echoed here, and this paper's from 2012. So I thought that was interesting. But it does say spend a lot of time on feature engineering, which is kind of contrary to what's working with neural networks, where you don't know the features, you just want more data, more parameters. I personally believe that feature engineering, when you can get the right amount of information gain and encode knowledge that's relevant, is incredibly valuable. But again, I'm not a researcher. So too many features, though, can cause this problem of dimensionality, where there's more features, it becomes harder to generalize because you need exponentially more data. And also, as you add features, the data in space is growing further and further apart. So having any ML algorithm pattern matching on that becomes more difficult. But more data can fix that, or if you reduce the dimensionality using various techniques to reduce the number of dimensions, or if you feature engineer in a way that encodes knowledge and you can remove some noisier dimensions, you can try to avoid or eliminate as best you can the curse of dimensionality. And then you're trying to balance the model complexity, where there's this sweet spot between being underfit and overfit that you're trying to find. Overfit means you are predicting the training data extremely well, but you can't generalize at all because you basically have just overfit to the training data. And underfit means that you didn't learn enough. You're too simple. It's not able to generalize outside the training set, but you're not even doing the training set well. You didn't train enough. And that is all. I hope you enjoyed this video. I hope you enjoyed this format. I'll try to make these videos more interesting. So please, any feedback on the style of the video, on the mind map, on the particulars of what I maybe missed or what I said. Thank you so much for watching. I'll see you in the next one.